Good afternoon, everybody, and welcome to the second week of the lectures for CS 1100. So, today is our fourth lecture, and let's recap what we have done in the last week and what we want to do in this week. So, the earliest lecture, the first lecture, we did a lot of fun exercises where you were introduced to programming your friend and then programming the turtle, which I hope you are also exploring on your own. Some of your classmates are sending me some of the patterns. Once I have a set of good, nice patterns to display, I will put them on the course homepage. Then in the third class, we saw a very simple C program, and you extended that program in the lab, and in fact did more than what was taught in the classes, which is again expected because most of you are exposed to programming. And what we are going to do this week is we are going to look at more of programming, of course, but at some of the things that we will need about the computer in general, or computing on a computer. We are going to visit them. This view will be a very high level view, a bird's eye view, but it will be a view which will be sufficient for us to understand what we are doing in terms of our programming. We'll also be talking about the memory and the processor. Again, at a very, very high level, we can't go into the details of the computer as a circuit and so on. But we will introduce the view that is required for the programming purposes. And then we will talk about memory and variables. Finally, we'll talk about input and output in C. That will be in today's class. And that is where some of you got stuck, where you did not know how to take input. And then we will move on to other things which may be very familiar to you, the assignment and other operators, but we will point out some things that sometimes are missed out or are some things which are specific to C. So this is the plan. Towards the end, we will go to modifying control flow using various constructs like the if, then, else, and so on. Okay, great. So that is what we did in the previous week and what we plan to do in this week. So before I get into the details, I want to share what we learned from the lab that we had for the first lab. And the lab was specifically designed for us to uh, understand the exposure of the class to programming. So as all of you would have observed, we had 3 questions which tested different skills that a different exposure for you in the C programming language. So the question 1 was a basic print statement, which all of you would have gotten right. Question 2 could have been done only with print statements, but all of you saw that it could be done with loops. I mean, a majority of you saw that it could be done with loops, which is very good. And since you know loops from either C++ or C or Python, you have conveniently used them here, which is very good. So again, Q2 was fine. Then Q3 was a statement which could not be done without a scanf or an input statement, which some of you, or I should say about, let's say we'll see the statistics, but a reasonable fraction does not know, but that's fine. I mean, it's just a specific command that you need to learn in C. So yeah, so I have the statistics here. So out of the 184 odd students that we have in the class, 174 attended. So the people who did not attend the lab, I must urge you that you should get in touch with your TA if you have not already told him or her, and you should explain the reason why you were absent. Otherwise, there will be some amount of penalty that we will have to levy. The same also holds for classes. If you miss too many classes, we will have to we'll have to understand what is the reason. There can be genuine reasons, but please be in touch with your TA or with me. Please inform me accordingly. Anyways, so amongst those of you attended, almost all of you solved Q1. If you did not solve Q1, for some reason, we will get back to you, and you should also proactively tell us what was the reason you couldn't solve Q1. Q2, again, everybody would have solved it, but 150 of you did it with loops, which is very good. And Q3, which required a scanf, 104 of you have done it. So the others, at least with the people whom I have interacted, because I was being TA for one of the groups, I realized that most of you could have done it in another programming language that you knew, but you did not simply know the scanf statement, which is fine, which we will teach you, but which is very, so this tells us that the class is at a very nice level of exposure to programming. As we have already seen, the exact language is of little concern. Your programming exposure and your understanding of solving problems is much more important than the language. We will be teaching you the language as we go along. That is the whole goal of the course, right? So having said this, what do we learn from this lab exercise? That a large fraction of you already know basic constructs of programming, so which is good for us. We don't have to work around the syntax of the basic programming constructs. Does it mean that people who do not know some of the basics will be at a loss? No, we will be covering everything, but the treatment will be rather in depth than being introductory. So at some points, if some of you feel that, okay, this has been at a slightly faster pace than what I would have liked, please get in touch with me or the TA or the class TA, and we'll be very happy to go over some things at a different pace for you. But in general, what we understand from the class is that most of you are at a very nice level of exposure to programming. So we will be able to do significant amount of things in the course as well as in the lab. So having said this, now let's set our goals for today. So our goals for today, which are the end goals, are like we want to play around with this printf statement. We have done very less with the printf statement in the last class. And of course, we want to understand the syntax and the semantics of the scanf statement. The same is with the printf statement. Of course, the printf we have used a little bit, but we will be going into the details of it and understanding usages of that in today's class. But to do all of this, we need to take a slight detour. This doesn't seem to be immediately relevant to programming. As I said, it will be a bird's eye view of computing on computers. But as you will see, when we go along, we will need some of these pieces, and those are the exact pieces that we are going to introduce, right? So for some of the part of the class today, we'll be talking about more on computing on computers, representation of numbers, and so on, and we'll see how that fits into the bigger picture. Okay, so this is our very, very high level view of the computing machine or our computer. There are many units. In fact, a computer is a huge electrical circuit with several units, the processor, the network units, several wires going around. But this is a mental model that we will be using. So what do we have? This memory is a contiguous chunk where you can store things. And you can also think of it as your blackboard, where you can write down things, or a sheet of paper where you can write down and store things. And there is a processor which can look at cells of this memory and do something with it. So what it does depends on what is present in that memory. And as we have already said, that computers only understand binary. So everything that will be there in this is going to be zeros or ones. This is what is our model of the computing machine or the computer. And all information, that is numbers, text, videos, audios that we want to process are brought into the memory, and then some processing is going to be done. In fact, our programs are also, while they are written on the files and they are present in the hard disk, but they are brought into the memory when they are to be executed. So as you see, on the left hand side, we have given some space for the program that we are executing. And then there is also data that on which the program is going to be executing. And all of them, all of these things reside in the main memory, right? Okay, great. So, so what does it mean when you want to say that I want to solve a problem using a computer? So what are problems that we want to solve? So some of the problems that we want to solve are, let's say, analyzing some lot of data about, let's say now COVID. So we want to analyze data about COVID. Where are the spikes? Where is it going extremely high? How are the percentage rises and all? These are already numbers that are there, so which is good. But there are also things like graphics, images, videos, and let's say even text things, text processing that you want to do. So how does the computer represent things? So the first thing is, in some way, the information that you have, either it is an image or a big document or anything that you want to process, is digitized. That is, it is broken down into smaller parts and finally represented as a number. Right? So everything that we want to the computer to solve or understand has to be converted into first into small parts and then finally represented as some number which the computer understands, and that number itself finally has to be represented in a language that the computer understands, which will be the binary. So we'll take a very simple example, which is representing text. So text is what we all understand. All of this that you see on the slide is text. But let's take a very small example. Let's say these two words, hi, Heather, where hi is followed by a comma, and then there is Heather, which is punctuated by a full stop. This is the text, or these are the characters that we want to store. So every character, including the punctuation symbols, including the even the space, is going to be represented by a unique symbol, which is unique, not symbol, unique number is given a unique number, and this number in fact has this number is standardized, and this is called the ASCII code, or that, and this whatever I'm showing you is the ASCII table. All of you may be already familiar, but just to reiterate, every character that we want to represent is given some code or some number, and that number is the ASCII code for that character. And in fact, as you may expect, the uppercase and lowercase have different codes. Some of you may already know these codes, and if you so this is how you are going to convert a text a text document or text segment into a number. So as we see here in the previous slide, if you look at capital H, it has been represented by 72. Where is it coming from? It is exactly coming from the ASCII code of H in this table, which if you look at here where I am pointing it out, it is going to be 72, which is the decimal value of this ASCII code. There is also hexadecimal, octal, and so on. I'll come to the number systems, but this is why we have written 72 here, and so on. So if you look at anything else, the full stop, it has been given 46, and that is again coming from the ASCII code for the full stop, which is 46. Right. So this is how we are going to take a character string or a set of characters and convert them into numbers. So whenever we want to talk about hi Heather, it will be represented by this set of numbers in this order. But this is about characters. How do you represent, let's say, an image? You take the image, let's assume for the moment it is black and white. If it is black and white, then you just put a grid on that image. The grid will have certain cells which will be black, and certain cells which will be white. There will be also certain cells which will be partially black and partially white, but you will convert them into either black or white depending on some kind of a rule that you will follow. That is, so much percentage of it is black, then it will be called as black, and so on. So then you have the image converted into image which has been digitized, or you have added a grid on that, and using that you can just convert it into a sequence of zeros and ones in that appropriate matrix. And as you can imagine, if you make the grid finer and finer, you will get a better and better representation of the black and white image that you want to represent, right? So once you know how to represent a black and white image, you can also think of other things that you want to digitize. But what is the main takeaway from here? Whatever you want to process on the computer, you have to first convert it into numbers and then feed it to a computer, and then the computer is going to process these numbers, right? So but then the question that we need to ask is, how are these numbers themselves stored, right? So all of us always work with numbers in the decimal system, where we use the symbols 0 to 9, and this is not something that I need to talk about. There is also a unary system where there is only a single symbol, which is 1, and I mean that is only a representative one, but you can take any symbol, but there's only a single symbol, and then everything has to be represented using this. And as you can imagine that if you have just this, the length of the code that you have to come up with for anything is going to be very, very large, because if you want to represent, so I mean, yeah, as the number of things that you want to represent increases, you need to increase the length of the code, because that is the only way you can do anything with the unary number system. We also have what is called as the binary number system, where we have two symbols which are zeros and ones, and this dramatically changes the uh, uh, length of the code that is required to represent the number of elements. So for example, if you want to represent k things, uh, k different things using this binary code, then you know that you require only log k log k length code for representing this, and using this you should be able to represent all the k different distinct things that you want to represent. So log k, when I say log k, the base is 2, because because we are using the binary number system. So this immediately begs the question that, okay, if you have this binary number system, if you increase the number of symbols, then it is very likely that the length of the code decreases. That is true. You can have an octal number system, you can have an hexadecimal number system, where the number of symbols increases. For example, in the octal number system, you have 0 to 7. In the hexadecimal number system, you have 16 symbols, 0 up to 15, but finally the 10 to 15 are represented using A and F, A to F, and you must have seen these hexadecimal numbers also. But so we'll see why we can only deal with one of the number systems, which is the binary number system. So just a very, very quick recap of what is this number system in a base n. We all know what a number represents, number means in decimal. That is the example given here is 329. So if you have this number 329, it means that 3 is in the hundreds place. Therefore, the number that is represented is 3 into 100 plus 2 into 10 plus 9 into 1. This is almost like a letdown. I should not be teaching it here, but just for the sake of completeness, I am mentioning it. But in the binary number system, if you look at a number which is 101, 329 cannot be a number in a binary number system. It can be a number in a hexadecimal number system, not even in an octal number system, but in a hexadecimal number system, this 329 can be a number. But in a binary number system, if you have the number 101, then it means that it is 1 into 2 to the power 2, which is 4, plus 0 into 2 to the power 1, which is 2, and I mean 0 into 2 to the power 1, which is 0, and 1 into 2 to the power 0, which is 1. So this is the representation of our decimal 5. So again, converting this decimal into binary or binary into decimal is something that all of you can do it. In fact, soon we will write programs to print out the decimal representation of a binary input and vice versa. But this is something that you should be aware that you can easily convert, and you will be in fact yourselves writing programs. So this is again something that if at all you have forgotten, you can recall how you convert a number from decimal to binary and vice versa. But once you have this, you know that every number that, so we have taken all the data that we want to process, somehow we have converted them into numbers. And now these numbers themselves are going to be represented by in some number system. And this number system that we are going to choose is going to be the binary number system. So why binary? As we said that unary will lead to very long lengths of the length of the codes that we will have to use. Binary makes things very compact. One can always ask that can we go to a richer number system where the codes will be even smaller or compact? Yes, one can, but the practical implementation of these number systems is harder. So in fact, as you know that this 0 and 1 is represented by the voltage on wires, and if you have fewer number of different values, then it is easier to store. Therefore, just having two different voltages, that is two different values of these voltages is something that has been found out by experience. That is a good thing. Therefore, we'll be sticking to this binary number system throughout because that is what the computers use. And in fact, other number systems can be encoded. You can easily convert from the one number system to the other. And again, these things can be written as programs, that is octal to hexadecimal, hexadecimal to binary, binary to decimal, and so on. And you will be in fact writing these programs as you go along. Okay, so what are our takeaways from whatever we have discussed? To solve anything on a computer, we need to represent it as a number. The numbers themselves are represented in some form of binary. Why do I say some form? Because the actual form that is used is not exactly what I have told here, because note that we did not even talk about what do you do for the sign of the number. You'll have positive and negative integers, you'll have fractional values and so on, but we have not spoken about that. At the time when it becomes relevant, we'll make some remarks about them, but there is some form of binary that is used, and the actual form is the one which is appropriate for efficient manipulation. You can we'll leave it at that point. And as we have already seen in the previous class, the programs themselves are converted into binary. We write a high level program which is in a language which is kind of English readable, but when the computer takes it up, it is going to be converted into a binary. So the programs themselves are represented as a binary string, right? So this is how everything that we want the computer to do or process is going to get converted into binary. So both the data and the programs are represented as binary in what we know as our memory. Memory, which we called as some place where we can store things. Think of it as a blackboard, and these cells as small places where you can store things which are either your variables or your program or whatever you want to store, or your images, right? So this is the model of computing that we will keep in mind, and if required, go back to it. If required, at some point we'll refine it and we will add details to it, right? So this is the model of computing that we will have throughout this course. More or less, this is the model which will be sufficient for us. Okay, so Before I go to our goals again for today's class, I want to introduce some terminology which is useful for us. So when we say that a control is at a particular statement, it means that, so we know that a program is a collection of statements which are, or commands which the computer knows how to execute. We have already talked about the computer being trained in a particular set of commands or a language, which we said that it is a little bit of abuse, but it means that it has a compiler for that language. So now when we say that the control is at a particular statement, it means that this statement can be a high level statement like our statement where we told the turtle to move forward, or it can be a very low level statement of a binary this thing, or an assembly language command like move this value from this register to another register. But when we say that the control is at a particular statement, then the computer is currently executing that statement. The control flow is the order in which these statements are going to get executed, and analogous to how we read documents from left to right, from top to bottom. Similarly, the execution of a program goes from top to down. However, that if you just have the program being executed sequentially, then to do things like what you wanted to do in case of, let's say, drawing a decagon, you have to write multiple statements, and that is quite repetitive and also error prone. So we already know that there are control flow modification statements, like we have seen the repeat statement or the loops that you know how to use, and these will allow you to change the flow that is going sequentially to possibly moving from one place to another, possibly repeating a set of statements or going and not executing a certain set of statements. Okay, a variable, as you are aware, is something that is an entity which is used for storing data, and variables also have types, as we'll come to it soon. And the whole computer memory, you can think of it as a blackboard, and the variable is a region in the blackboard where you can write a value, where you can read that value, and that region is given a name which is called the variable name. And once we give that some name, we are going to always use that name to refer to that value in that cell or place where you have written, right? So these are some things that we will use interchangeably. We will use repeatedly during the discussion. So I wanted to introduce these terms. These are not very new for all of you, but just wanted to make sure that we are on the same terminology. Okay, so now we come back to our goals for today. And as we said, the goals for today were, in fact, the end goals were playing with the printf statement. So this, the end goals were playing with the printf statement and understanding the semantics of the scanf statement. But we took a small detour. We understood how the computers, what is the high level view of our computing machine. And now we come back to talking about the printf statement. Okay, so before we talk about the printf statement, I want to talk about variables. Now that we know that variable is a cell in the memory where, or place in the memory where we are going to write down something. And when we say that a variable is of a particular type, and you know that there are different types for variables, what does it determine? It determines how much memory is allocated to that variable. And once you write something into that memory location, how does one interpret that bit pattern? So sorry, there is a typo here. How does one interpret that bit pattern in the memory location? So that those are the things that we want to tell by telling what is the type of the variable, right? So the commonly used data types or variable types are integer, char, char for character, int for integer, and float for floating point values. There are also others that you may be aware of, unsigned int, double, and so on. We'll come to it as we need it. But at the moment, let's illustrate things using these different data types. Okay, so now this is the first time we are using the printf statement with the really the format specifier. So now this is a C program. So I hope you have come to your comfort zone where you are now thinking of, you are now again looking at programs rather than looking at a model of computation and so on. So this is the familiar C program. We have defined a variable ch. This is the name of that variable, and ch, which is of type character. What does it tell? The type tells it that it has to give certain amount of memory. Typically characters are given 1 byte of memory storage, and whenever you write some bit pattern, it is going to be interpreted using the ASCII code that we have already described. So this we have initialized this memory using the character lowercase a, which is shown in this line, and then in the next statement we are printing the character. This print is done using the following. So there is a constant string that we are printing, which we did earlier also. We had printed asterisk. So this is the characters this is a constant string. The new part possibly for some of you is this %c, which is telling telling that the variable that I'm going to see after the comma is going to be of the type character, and that is why that C is coming in, and the /n is simply for the new value, new line character that you want to print in. So what this the format specifier has this percent and some character which determines the type of the variable. For example, if you say %d, then it assumes, it expects that at that position you are going to give a integer. If you say %f, then it is expecting a floating point data type variable that you are going to give, right? So I'm going to tell the general format of the printf. So the printf command or function, whatever you want to think about it, in fact it is a function, has the following form. It has a format string, and we will say what the format string contains, followed by some number of variables. And if it has n number of variables that you want to print, then the format string should have n percentage values followed by the appropriate character. So the format string, as I said, specifies how many variables to expect. So if you have n, if you want to print n variables, you should have n % something something. So %c for character, %d for integer, %f for float, and so on. Then the type of each variable, that is what I said that the d or c will specify. There is also a width parameter and precision parameter, which if applicable are given, and we will see some examples of that. Just to bring to your attention, people who are using this printf for the first time, you will make mistakes in the comma, which may be missing after the double quote. So this format string is given in double quotes, like we had given the asterisk in double quotes. It did not have any percentage, so we did not give any variable. Then if you give just 3 percentages but give 5 variables here, then this is a mismatch in the number of variables expected and given. Or you could do it the other way, that is you give 5 percentages in the format string with appropriate type of each variable, but you want to print 7 variables, which is also incorrect. So you should take care of matching the number of actual variables given and the expected variables, right? Okay, so one important point to note here is that typically when we think of functions, these functions are having a fixed set of parameters. For example, when we saw repeat, it took as a integer value which told how many times this statement has to be repeated. So it took one argument, right? So that is what is called the argument of a function. Similarly, forward, it took as the number of pixels that the turtle should move, or left, it took the number of the degrees by which the turtle should move to the left, and so on, or wait. So these are functions, or you can think of functions that you have studied in your 12th class, which are like sine of x or cos of x or square root of y and so on, which take in one value and which take in some value or a fixed set of values and return some value. Let's say it can be an integer, it can be a character, it can be something else, but it takes a fixed set of values. On the other hand, the printf function that is here takes in variable number of arguments, and this is something very peculiar about this printf statement, the printf function. You will see that this applies for the other function, which is the input statement, which is the scanf statement, that also has a variable number of arguments. And this is very helpful because we can now print any number of variables using this single printf statement, right? So that is very helpful for us. So you will see examples of this as we go along. Okay, so having said this in a generic form, now let's state what is this, what is the exact format specifier. So this percent will be followed by W, which is the width, which is an optional thing. P, W dot P, which the dot is something that you have to give, dot P, and then the conversion character, which is C. Since W dot P are optional, these are many times not given unless you are very specific about how you want to format your output. These are ignored. So the way you are going to write your printf statement is always going to be printf percent dx, where x is an integer, printf percent little c char, where ch, where ch is a variable of type char, or printf percent f1, where f1 is a variable of type float. So the conversion character capital C, which is the placeholder here, are the different values that it can take are D for integer, as we have been saying, and so on, X for hexadecimal. So you can write an integer X as some value, and if you want to print its hexadecimal value, you can print it as percent X, the integer, and it will print out the hexadecimal value for you. So as you use this printf statement with the format specifier, you will get more and more used to it. So there's nothing to learn by heart. There's nothing about programming here. It is about knowing the way this printf statement works. And at times when you require to use it in a particular way, that is give out nicely formatted things, you should be able to use it with the width and precision specifiers that are given to you. Okay, so just to make sure that you understand these width and precision specifiers. So as I said, if you have a floating point, if you have something which is a float value and you want to print it out, if you simply say value, the value of f1 is percent f1, which is the most regular usage of it, it will just print out 23.4290, whatever is given to it. If you say you want 0.3, which means that you just want three decimals after the precision of 3 after the decimal point, then it is going to print out 23.429 429 and ignore the 0. In fact, the 0 here is frivolous, but it could have been 9 3 and still it would have printed out 23.4299 as the value. And if you look, you should try out what happens when you give the value of f1 is %20f. This is not the same as 0.3 or something. It means the width is 20. It means it is going to give 20 width to print this. Therefore, since this has 1, 2, 3, 4, 5, 6, 7 already 7 characters already in it, it will add actually the appropriate number of blank spaces, most likely 13 blank spaces, to make the whole thing as 20, and then it is going to print it out. So you will see that there will be a set of leading blank spaces if you print out the this in this format. So you can play around with this width and precision and print out numbers in different formats. Again, one can always ask whether this is very important. According to me, this is something that one needs to play around only when you need it. You need to know about this. The important parts is you can format input, format output the way you want, but the details of this are something that you can look up when required. So this is not something that I feel is a integral part of programming, but it is something about the details of the printf statement, which is good to know when you need it, but it doesn't hurt if you have forgotten some of these things at some point of time. Okay, so another example is you are having an integer x, its value, sorry, z, whose value is 20, and if you simply print %d/n/z, then it is going to print out 20. If you print out %o, then it is going to print out the octal representation of 20, which is going to be yeah. So it will be 14 because it will be 8 sorry, so yeah, it will be the octal representation of 14, just figure it out. And similarly, there will be an hexadecimal representation of octal representation of 20 and the hexadecimal representation of 20, which will be printed out as a result of this, right? So this is what the program is going to do. So now we come to the part where some of you were stuck in the lab, which is the input statement. And the input statement, having seen the output statement, is going to look very similar, but I will point out the most important difference. So it again has a format string, which allows you to take in multiple variables at the same time. But it says variable 1, variable 2, variable n the same way, but please note that there is a and preceding each of these variables, and I'll come to it and tell why the and is there. It will become more obvious when we talk about functions in detail towards in the middle of the course, but it is important to note that there is a and in the variables, and that tells us what is the address of that variable rather than telling the variable itself, right? So so the format string has the same meaning, that is it will tell how many variables to expect. If you have 3 percentages, it means that you want to take in 3 inputs. If you say the first is %c, it means that the first is a character. If you say the second is a %c, again the second is a character. If you say the third is a %d, it means that the third is going to be an integer. But when you give the names of these variables, let's say ch1 is the first character, you are not going to say ch1, you are going to say and ch1 and ch2 and z, assuming z is the name of the integer variable, right? So a very common mistake when you are using scanf for the first time is to forget writing the and simply write it as a printf statement. And on Linux machines, this is the first time you will get what is called as segmentation fault core dump. And when you see it for the first time, it is quite irritating. But this is something that you will eventually face either here or somewhere during your programming. And typically, in fact, when you even write this without an and, you are going to get a warning from the compiler. You can choose to ignore it and then get a runtime error. But if you pay attention carefully to it, you will see that it says that it expects an address, whereas you have not specified an address. Okay, so as I said earlier, like the printf statement, the scanf also takes in variable number of arguments, as is seen in this scene here. And a very simple example of scanf and printf is you have the input, you have an integer variable z. Since it's an integer variable, you are going to take in it as a %d. And please note the and preceding the name of the variable, which is z. When you are printing it out, the and is not needed. In fact, you should not use it because you're not printing the so let me just say what the and means. It tells the function that you are not the and preceding the variable tells that it is the address of the variable rather than the variable itself. And why is this address required is something that will become more evident because later, but I'll briefly say it now. Whenever in C you are passing arguments, they are passed by what is called as value. That is, a copy of that is made, and that is passed to the the function. So if you did not specify the and, it means that it is going to take it and copy it to some other cell, and a copy of that is going to be given to that function. The function is going to write that value in that copy, and you are not, and when you return back to your main function, the original place where you wanted z has not been modified, and that is what will cause the problem. Therefore you are going to therefore you're going to have issues if you forget to write this and. So you must try it writing without an and for your understanding purposes. See what happens or when you do it on the program. And we'll come back to this as we do more and more programming, and we'll see why this and is something which is very peculiar to the C language that you have to give in. And this is because if you have seen earlier pass by value versus pass by reference, this is why you are having to send this address here, whereas in some other languages it is you can do it without the address of the variable, right? So with this I will stop here. You can try out these examples and experiment with things that I mentioned as common mistakes and so on. Okay, thank you.